Modern aviation is honestly a field of constant innovation, where the performance, efficiency, and sustainability of aircraft depend intrinsically on the sophistication of their engines. These complex machines are really the pulsating heart that enables global connectivity, cargo transport, and air defense. So this article aims to provide a comprehensive analysis of the main engine types used in the global aviation industry, detailing their operating principles, technical characteristics, applications, financial cost benefit, and environmental impact, with a focus on future perspectives for a more sustainable aviation. Turbofan engines are, without a doubt, the backbone of commercial aviation and many military transport and patrol applications. They represent a significant evolution from turbojets, incorporating a large fan at the front. A turbofan operates by drawing a large amount of air through the fan. A portion of this air, known as bypass air, bypasses the engine core, generating most of the thrust, while the other part enters the compressor, is mixed with fuel in the combustion chamber, burned and expanded through the turbine, generating energy to drive the compressor and the fan. The hot exhaust air is then expelled through the nozzle. The key components include the fan, low-pressure compressor, often called N1, and high-pressure compressor, or N2, the combustion chamber, high-pressure turbine, low-pressure turbine, and the nozzle. Now, when it comes to technological innovations, high-bypass engines are predominant, optimizing efficiency for subsonic flights, with about 80 to 90% of the thrust generated by the bypass air. Advances in composite materials for fan blades and ceramics for the core increase resistance to high temperatures and reduce weight. The geared turbofan allows the fan and low-pressure turbine to rotate at different optimal speeds, which increases efficiency and reduces noise. For performance parameters, thrust varies from tens to hundreds of thousands of pounds. For example, the GE90 of the Boeing 777 can generate over 115,000 pounds of force. Specific fuel consumption is low compared to turbojets, making it ideal for cruising at high altitudes above 30,000 feet and subsonic speeds, typically Mach 0.75 to 0.85. The ideal operating altitude and speed are high altitudes to minimize drag and high subsonic cruising speeds to maximize bypass efficiency. Turbofans offer a superior balance between power, fuel consumption, and environmental impact compared to turbojets. The large volume of air passing through the bypass contributes to more economical consumption and makes the engine significantly quieter as it dilutes and reduces the speed of the exhaust jet. The advantages include excellent fuel efficiency at cruising speeds, lower noise, and greater thrust capability for short takeoffs. Disadvantages are, greater complexity and weight than turbojets, and a larger frontal diameter, which can increase drag at supersonic speeds. In terms of applications, turbofans are dominant in commercial transport aircraft like the Boeing 737, 747, 777, and 787, as well as the Airbus A320, A330, A350, and A380. They are also used in military cargo planes, such as the C-17 Globemaster III, and some combat or patrol aircraft that prioritize range and efficiency, like the P-8 Poseidon. Although, The initial cost of a turbofan engine is pretty high. An Airbus A320 engine can cost around 10 million US dollars. Its efficiency actually results in lower operating costs for airlines. Maintenance costs are, also high due to the complexity of these engines, but that's offset by long intervals between overhauls known as TBO, or time between overhaul, and by the high reliability of the engines. Excellent fuel efficiency is really the main factor in reducing operating costs, ensuring a good return on investment, because airlines can transport more passengers per kilometer with lower fuel consumption and ultimately a lower cost per seat mile. Turbofans produce fewer pollutant emissions per unit of thrust and are noticeably quieter compared to turbojets. When we talk about emission levels, they're comparatively lower, thanks to optimized combustion and the high bypass ratio, which help reduce nitrogen oxides and particulate matter emissions. Carbon dioxide emissions are directly linked to fuel consumption, so efficiency is absolutely fundamental here. In terms of noise, turbofans are significantly quieter than turbojets, which really helps minimize the impact on communities living near airports. There are also several key initiatives and technologies shaping the future. For example, the use of sustainable aviation fuels, or SAFs, can reduce carbon dioxide emissions by up to 80% over their life cycle, and these fuels are fully compatible with existing turbofans. New engine architectures like CFM International's RISE program are exploring open fan or prop fan designs for even greater propulsive efficiency and reduced emissions and noise. Plus, turbofans are being adapted to incorporate hybrid electric propulsion elements or to operate with hydrogen, either through direct combustion or by using fuel cells, which represents the future of sustainable aviation. Looking ahead, turbofans will continue to be the predominant engine in commercial aviation, with an increasing focus on new architectures, advanced materials, digitalization for predictive maintenance, and operation with alternative fuels, all to help achieve aviation's decarbonization goals. The turbojet was actually the first type of jet engine to be widely used, and it really marked the beginning of the jet age in aviation. Its conceptual simplicity made it revolutionary for speed. So, a turbojet draws air through the inlet, compresses it, then injects fuel and burns it in the combustion chamber. The hot, high-pressure gases are expanded through a turbine, which, by the way, drives the compressor, and then expelled at high speed through the nozzle, generating thrust. There's no cold air bypass in this setup. The key components you'll find are the compressor combustion chamber, turbine, and nozzle. Now, when it comes to technological innovations, there honestly haven't been many recent advances for mainstream aviation since the focus has kind of shifted to turbofans. Afterburner concepts, though, are pretty common in military turbojets for temporary thrust augmentation. Looking at performance parameters, turbojets deliver high thrust for their size, especially when afterburning is used. But their specific fuel consumption is very high at all altitudes and speeds, making them less efficient than turbofans. Turbojets really shine at high altitudes and supersonic speeds, where the Brayton cycle efficiency is well optimized. turbojets were absolutely crucial for the development of aircraft that could reach extremely high speeds and altitudes. However, they do have some pretty significant limitations at low speeds and altitudes where their efficiency drops off drastically due to high fuel consumption. If we look at the advantages, turbojets offer excellent high speed or supersonic performance, a smaller frontal area which is great for combat aircraft, and a certain mechanical simplicity. On the flip side, they're extremely noisy, fuel inefficient, especially at low speeds and altitudes, and they produce low thrust at low speeds. As for applications, turbojets have been used in military jets and some early commercial aircraft like the Messerschmitt Me 262, a Gloster Meteor, de Havilland Comet, and early versions of the Boeing 707, but honestly, they're practically obsolete for commercial aircraft now, mostly because of inefficiency and noise. And they've been replaced by more efficient turbofans. The high specific fuel consumption of turbojets makes them, well, less economical for most flight operations, which results in really high operating costs. Their use is justified only in situations where high speed and performance are absolutely critical, like in combat jets, where fuel cost is kind of secondary to mission capability. Turbojets are known for their high noise levels and higher pollutant emissions compared to turbofans, mainly because they lack the bypass flow that helps dilute and slow down the exhaust jet. When it comes to emission levels, they are pretty high, with greater pollutant emissions per unit of thrust, mostly due to lower efficiency and less optimized combustion. Noise-wise, turbojets are extremely noisy, especially during takeoffs and when afterburning is used. Looking ahead, their relevance is progressively diminishing. They're being replaced by more efficient, low bypass turbofans or by specific engines for 5th and 6th generation aircraft that optimize stealth and supersonic performance. Honestly, there is no significant focus on making turbojets greener for a sustainable future in commercial aviation. Turboprop engines are actually a variation of jet engines, designed to combine the efficiency of a propeller with the power of a gas turbine. This makes them ideal for lower altitude and speed flights. In a turboprop engine, the gas turbine operates pretty much like it does in a turbojet, but most of the energy from the exhaust gases is used to spin a power turbine. This turbine in turn drives a propeller through a reduction gearbox. The propeller generates most of the thrust, about 90%, by moving a large mass of air at a lower speed, while the remaining 10% comes from the residual jet. The key components include the compressor, combustion chamber, turbine, reduction gearbox, and, of course, the propeller. Technological innovations like advanced propeller designs, think scimitar or multi-blade, help reduce noise and increase efficiency. Full authority digital engine control, or FADEC, is also used for performance optimization. When it comes to performance parameters, thrust is measured in shaft horsepower, or SHP, delivered to the propeller. And these engines generate high static thrust for short takeoffs. Specific fuel consumption, or SFC, is very low at the right speeds and altitudes, generally below 25,000 feet and cruising speeds of 250 to 350 knots. Overall, Turboprops are excellent for short to medium haul flights, regional operations, and at lower altitudes where air density is higher. So, turboprops are more fuel efficient than turbojets and turbofans when flying at lower speeds and altitudes. They also offer excellent short takeoff and landing performance, which really makes them suitable for operations on smaller or even unpaved runways. Among their main advantages, you'll find exceptional fuel efficiency at lower cruising speeds, excellent stall performance, and of course lower operating costs for short routes. But there are some disadvantages too. Their cruising speed is limited, generally below 400 knots, and they fly at lower altitudes, which can sometimes result in more turbulent flights. Oh, and they can be noisier for passengers because of the propeller sound. In terms of applications, turboprops are dominant in regional aircraft like the ATR 42 and 72 and the de Havilland Canada-8. They are also widely used in medium-sized military transport aircraft such as the Lockheed C-130 Hercules and the Embraer KC-390 Millennium, as well as in maritime patrol aircraft like the P-3 Orion. The fuel efficiency of turboprops, especially within their ideal flight envelope, really translates into operating cost savings. Their initial cost is lower than that of similarly sized regional jets, and maintenance costs are pretty competitive, with good reliability as well. Overall, they provide an excellent return on investment on regional routes, which allows smaller cities to be connected more economically. Turboprops consume less fuel at lower speeds and altitudes, and this definitely contributes to reducing their environmental impact. When it comes to emission levels, they're quite low thanks to high fuel efficiency for their application. This means a smaller carbon footprint per passenger kilometer on regional routes compared to jets. Now, propeller noise is a prominent characteristic, but it's been mitigated with more advanced and quieter blade and propeller design. Looking at initiatives and technologies, turboprops are ideal candidates for hybrid electric and all-electric propulsion for regional and short-haul flights, mainly because of their efficiency at lower speeds and the relative ease of integrating electric motors with propellers. So the outlook is quite promising. Turboprops are expected to play a key role in regional flights and as platforms for greener propulsion technologies, really contributing to the decarbonization of short routes. Although not primary propulsion engines for commercial or military fixed-wing aircraft, turboshaft engines are, absolutely crucial for rotary-wing aviation, like helicopters, and as auxiliary power units or APUs in large aircraft. A turboshaft engine is, a gas turbine that converts the energy of exhaust gases primarily into rotary shaft power rather than direct thrust. This power is used to spin a main rotor and a tail rotor in the case of helicopters, or to drive generators and auxiliary systems when we're talking about APUs. The key components include the compressor, combustion chamber, gas turbine, which drives the compressor, and a separate power turbine that actually drives the output shaft. Now, some of the technological innovations here are the small size and high power to weight ratio, plus really precise electronic control to manage variable rotor loads. When it comes to performance parameters, power is measured in shaft horsepower, or SHP, and that can range from hundreds to thousands of SHP. Specific fuel consumption, or SFC, is optimized for various helicopter flight conditions like hovering or cruising. And these engines are suitable for operations across a wide range of altitudes and speeds, especially for vertical flight and hovering. The primary purpose of the turboshaft is to generate mechanical power for a shaft, not direct thrust. The power turbine is usually free, meaning it is not mechanically coupled to the compressor turbine, which allows for greater operational flexibility. Some of the advantages include a high power to weight ratio, reliability, smooth operation, and the ability to operate with various fuel types. On the downside, they're not designed for direct propulsion of fixed-wing aircraft. In terms of applications, turbo shafts are used exclusively in helicopters like the Bell 206, Airbus H145, Sikorsky UH-60 Black Hawk, and Boeing AH-64 Apache, and as APUs in large commercial aircraft such as the Boeing 747 and Airbus A380, where they provide electrical and pneumatic power both on the ground and in flight. The initial cost of a turboshaft is high, proportional to its complexity and technology. Maintenance costs are also high, especially in helicopters, due to safety requirements and operational stress cycles. Their fuel efficiency is optimized for helicopter flight cycles, which are inherently less efficient than those of fixed-wing aircraft. They are essential for helicopter operations in various missions, like rescue, transport, and military, where vertical flight capability really justifies the costs. Similar to other turbine engines, CO2, NOx, and particulate emissions depend on the design and combustion cycle. There is continuous effort to optimize combustion and reduce emissions. Noise is a significant issue for helicopters, but the turboshaft engine itself is actually less noisy than the noise generated by the main rotor. Research to reduce fuel consumption and emissions includes the use of sustainable aviation fuels, or SAFs, and the development of hybrid electric propulsion for future vertical takeoff and landing aircraft known as eVTOLs, which may complement or even replace helicopters in certain urban and regional applications. Looking ahead, they will continue to be the standard engine for helicopters, with innovations focused on greater efficiency and integration with hybrid propulsion systems for new urban air mobility platforms. The evolution of aircraft engines reflects a trajectory of constant pursuit of greater efficiency, lower environmental impact, and better performance. From the noisy, fuel-thirsty turbojet to the quiet and efficient high bypass turbofan and the economical turboprop for short routes, the industry has really adapted to market demands and growing environmental concerns. Now, when it comes to key analysis points, there's always a trade-off between efficiency and speed. High bypass engines, like turbofans and turboprops, are more efficient at subsonic speeds, while turbojets excel at supersonic speeds. The choice of engine really depends on the aircraft's mission. Fuel cost is the dominant factor in the cost of ownership and operation. More efficient engines, like modern turbofans and turboprops, drastically reduce operating costs, which helps offset their higher initial cost and complex maintenance. Environmental regulations, such as ICAO Annex 16, have driven the development of quieter engines with lower emissions. The high bypass of turbofans is key to noise reduction, while combustion optimization and the use of sustainable aviation fuels are crucial for emissions. Each engine type has found its niche: turbofans for long-haul, high-capacity cruising flights, turboprops for regional and short routes, turbojets for high-performance military applications, and turboshaft for helicopters and auxiliary power units. The aviation industry is really under pressure to reduce its carbon footprint. Current engines play a vital role in this transition through several key areas. First, there's continuous efficiency improvement. New generations of turbofans, like geared turbofans and open rotors, promise additional reductions in fuel consumption and, as a result, in carbon dioxide emissions. Second, sustainable aviation fuels, or SAFs, are becoming more important. The compatibility of existing engines with SAFs is a pillar of short to medium-term decarbonization, and it leverages our current infrastructure. Third, we have hybridization and electrification. The development of hybrid electric and all-electric aircraft, especially for short routes and urban air mobility, uses electric motor technology either alongside or instead of smaller gas turbines. Turboprops and turboshafts in particular are quite adaptable to these configurations. And finally, hydrogen. Research into hydrogen engines, whether by direct combustion in adapted turbines or via fuel cells, represents a long-term prospect for zero-emission aviation. But it will require major changes in both engines and aircraft infrastructure. The future of aircraft engines is, well, pretty multifaceted. With the pursuit of efficiency and sustainability as central themes, we'll see the continuous optimization of turbofans, the expansion of SAF use, the emergence of hybrid electric configurations for specific market segments, and, in the long term, the possible transition to hydrogen propulsion. Collaboration between engine manufacturers, airlines, governments, and research institutions will be fundamental to overcome technological and financial challenges and achieve the ambitious decarbonization goals of global aviation. Aircraft engines are honestly engineering marvels that enable modern aviation. Each type, turbofan, turbojet, turboprop, and turboshaft, has unique characteristics that make it ideal for specific applications, balancing performance, costs, and environmental impact. The continuous evolution of these engines, driven by technological innovations and the growing demand for sustainability, really demonstrates the industry's ability to adapt and progress. The path to greener aviation is already underway, with engines right at the center of this transformation, promising a future where the sky remains accessible, but with a significantly smaller environmental footprint. And if you enjoyed this video, don't forget to like, share, and subscribe for more content. The information contained in this article was compiled and synthesized from web search results provided by OpenAI, including, but not limited to, the winged heart, a comprehensive analysis of aeronautical engines and their impact on global aviation. The main topic covers a comprehensive analysis of aeronautical engines, turbofans, turbojets, turboprops, and turboshafts, their principles, characteristics, applications, financial and environmental implications, and future perspective.